So let's take a look at Newton's equation. So what Newton actually said when he was talking about gravity was that we have a force of gravity. So this is the force of gravity. Force of gravity. And he said it was equal to m1 times m2 divided by the radius or distance between the objects squared. So m1 is the mass of the first object, m2 is the mass of a second object, and r is the distance between the objects. And he said basically that, so I have, for example, the Earth, and I have the moon, okay? So this distance of r, and then this object has a mass, and then this object has a mass. The force of gravity between them would be equal to this equation. Now later we had a scientist by the name of Miles Cavendish who came along and said there's actually this factor called G, and it's all because what Newton said was close, but it wasn't exactly correct. And so until Cavendish came up with the G, we've added that in, and now we have the gravitational constant, G, times m1 times m2 divided by r squared, and we get mass. We get the force of gravity. This may be familiar to some of you because you may have learned the electric force is K Q1 Q2 over r squared. So they're very similar equations, and it's this similarity, this pattern that we've noticed, that leads us as scientists to come up with ideas like string theory and looking for theories of unification, where we're trying to connect all these forces that occur in nature and describe them with one equation. We haven't done that. Even though they look similar, we haven't been able to do that quite yet. But our research at the Large Hadron Collider and the research we're doing surrounding the Higgs particle and all that kind of stuff is working towards trying to unify these two ideas, the electric force and the gravitational force, trying to put them together. Okay, so just like we did with this one, we're going to take a look at the math with this one. So let me move over here. So the gravitational constant, G, equals 6.67 times 10 to the negative 11th power. The units is newtons times meters squared divided by kilograms squared. Okay, so what does this times 10 to the negative 11th look like? So what this means is, well, let's take an example. If I do 1 divided by x squared in your math class, you should know that that's equal to x to the negative 2 power. So x to the negative 2 means I'm dividing by x squared. So what does this mean? This means that I'm dividing by 10 to the 11th power. So this is going to be a really big number with lots of zeros. And if I divide by that, I'm going to get a really, really tiny decimal. Okay, so what I thought I would do, because this is a conceptual physics class, when we are not going to actually do this calculation, I thought I would show you the calculation just so you would appreciate what's going on. So G times m1 times m2 divided by r squared. And what this is right here is I've taken a 1 kilogram bowling ball, and I've placed it on the surface of the Earth. So object 1 is the Earth, object 2 is going to be the bowling ball, and then we have the distance between them. So here's G, there's my bowling ball of 1 kilogram, here's the mass of the Earth, here's the radius of the Earth. I plug all those numbers in my calculator, and I get the force of gravity equals 9.8 newtons. So I did a bunch of math with a bunch of numbers to get 9.8 newtons. Force equals mass times acceleration. That's what we just finished looking at. So if I plug these same masses into this equation, I get 1 kilogram times 9.8 meters per second squared. I get 9.8 newtons. So the equation we've learned for the force of gravity on the Earth, okay, mass times the acceleration due to gravity, is equal to the same force using Newton's equation. Okay. So what I want to show you though is if this was not the Earth and this was the moon, we would get a much different number because the actual acceleration on the moon is 1.6 meters per second squared. And so we would get 1.6 newtons. Does that change the size of the bowling ball or the mass of the bowling ball? No. It just means that the moon's mass is less, so it's going to pull on it less. Okay, so mass doesn't change, but the acceleration can change because the mass of the other object can change. Okay, so let's take a look at some generic situations from a general standpoint, and I think this will make more sense.